And we will start with the current slide. Here it comes. Yes.
Are you not following?
Yes, I am.
I was just going to ask you a quick question.
I'm sorry?
I was just going to ask you a quick question. I got orientation right here. We're doing some sort of project. Well, I know we're doing it. She said we had to interview somebody, and I don't have anyone to interview based on my specific topic, which is biomedical engineering. And she told me to come ask you about it to see if you could help me. And so we can like talk about it.
All right. I'm in class right now,
Okay.
and I'll be out of this class at
11:40.
Yeah, 11:45 is when I get down to well, I usually don't quite get there by then, but then I have another class starting at 12:15. But the biggest block of time I have is between 2 and 6 to 9. Yeah, 2 and 6. Are you still on campus then?
Yeah, I'll get out of class till like 5:30, but I can see you in that 11:40, 12:15
Okay.
time.
Well, okay. How about tomorrow? Are you on campus tomorrow?
Yes, sir. What time?
Okay, 11:15. Wait. Yeah, 11:15 till 1:15. Is that bad for you too?
I'm gonna be in class until like 12:45.
Okay, well, you got 30 minutes there. Do you want to try to do it then?
Yeah.
Okay, now on Wednesday, and maybe same for you, 2 to 4. I mean 2 to 4 on Wednesday, not 2 to 6. And that's not good for you.
Yeah, I try to get you Tuesday, Wednesday, when I because 4 would be good for me because I got a class over the drafting and design build till 5:30 from 3 to 5:30.
Is that on Wednesday also?
Monday.
Okay, so that probably would be good. And then my Thursday's the same as Tuesday, 11:15 to 1:15. Okay, and then on Friday I'm on the Birmingham campus, 8 to 12. So pick your time. My schedule's on my office door. You know where my office door is?
Yeah, I visited that.
Okay.
Signs
We-
on the kitchen.
Okay, well you see the schedule there. So any of those times will do. Okay.
My name Ashton.
Is what?
Ashton.
Aston?
Yes, sir.
Okay.
Thank you.
All right. Somehow I just don't understand how I'm in class right now. It's taken the way it is. Like, oh, you're available to talk. No, I'm in class right now. But I'm not saying anything, am I? Especially on tape. Okay, never mind. All right. Let me just go over quickly the announcements. You've heard them all before about applying for graduation. If you have any questions about that, this is great. Ask me as soon as you can. Note takers needed for fall 2018. They will pay you to take notes for people, and the Space Center is looking to pay you to be a peer tutor in the areas of math, English, biology, computer science, and Spanish. And also on this campus, Student Support Services hires tutors as well. So you got 3 opportunities to make you a little money while helping other people, and basically sort of helping yourself on at least 2 of those. All right, now I had it marked that example 5 is where we're picking up this time. Is that what you had? And this is example 3. We've already done 3 and 4. 5 is on page 345. This is chapter 5, logarithmic, exponential, and other transcendental functions. And example 5 is finding the equation of a tangent line. Okay? Is that where you had that we were? Okay. Any questions before we get started here? Okay? So find an equation of a tangent line to the graph of f of x is equal to 2 plus e to the 1 minus x, okay, at the point 1, 3. Okay? Now, before I even begin, I'm a cynic. Okay? And I want to make sure that that point is indeed on this graph. Otherwise, I'm going to be trying to prove something that's not even true. Okay? So let's just see, is this point on this graph? The ordered pair 1, 3, what do those things stand for?
X is 1, Y is
X is 1. So if you put a 1 in here for the X, what do you get? 1 minus 1 is
0.
E to the 0 is
1.
1, and 2 plus 1 is 3. Yes, and the f of x is y, right? So yes, that point is on there. Okay. Now, it's asking for an equation of a tangent line. How is an equation of a tangent line going to look? What does the equation of a line look like? Okay, you're going to have a derivative somewhere, but I'm asking for what is the equation of a line? What does it look like? There's several different forms you could give me.
Slope-intercept.
That would be one. Okay, how would that look?
Isn't it y minus y1 equals x minus x1 plus b, something like that.
Okay. You just took two of them and sort of meshed them up together and messed them both up. Okay. Now, you were given me to begin with a point slope formula. When I have an x1 and y1 in it, that's a point.
Oh yeah, y equals mx plus b.
Ah, there's the other one. Y is equal to mx plus b. You want to go with that one? Okay, let me erase the other one. To make that one true, just put an m in front of the x minus x1. Okay, that would have worked too. Okay, in fact, you might have thought it worked better, but if you want to go with this one, we'll go with this one. So I'm going to erase everything here and go back to put the second one at the top. Y is equal to mx plus b. Okay. Now, you need to refresh my memory. What in the world is m?
Slope.
Slope. Okay. That's the slope of the tangent line. Okay. Slope of the line that you're talking about there. The line we're talking about is a tangent line. What is the slope of the tangent line? Back to your first answer. Slope of a tangent line is the...
Oh, the point slope?
No, not that. Go back even further. The slope is the slope of a line is its... The slope of a tangent line is the derivative. So, we can get the m there if we take the derivative of this one, right? Because the derivative is the slope of the tangent line. And we're going to evaluate it at that point, okay? So let's do our f prime. And what would that be? I heard a little something there. I didn't quite catch it all, but
well, the first part would be e to the 1 minus.
okay, e to the 1 minus x. Okay, number one, left off the 2 because the derivative of 2 is 0. Okay, so it's e to the 1 minus x, and then you got a negative. Yeah, negative in front, negative 1 in front. Exactly, because of the chain rule. Derivative of 2 is 0, so that's out of there. Derivative of the exponential function is itself, and then you do the derivative, the chain rule, derivative of that, and derivative of that is minus 1. So just put the minus in front. Okay? So there's the derivative at any point x. What is the derivative at 1, 3? So f prime at 1, when x is equal to 1, would be where?
1.
Not quite.
Well, yeah, it'd be 1. Or, well, no, it'd be negative 1.
Negative 1. Perfect. Okay? It would be a negative 1. Because, again, when you put 1 in there, you get 1 minus 1 is 0, e to the 0 is 1, but then the minus sign in front makes it a minus 1. So now we've got our m. This is our m. The derivative is the slope. Okay? So now we have y is equal to minus x plus b. Okay. Now here's where your other form might have been a little easier or not. It doesn't really matter. We just don't know what the b is, right? Agreed? We don't know what b is? Okay. But we know that this formula should be good for any xy pair on that line, right? Do we know an xy pair that's on that line? 1, 3. So let's plug in a 1 for x and a 3 for y, and what would that make it be? 3 is equal to negative 1 plus b. Now can we figure out what b is? 4. B is equal to 4. Now we go back and plug in y is equal to minus x plus 4. There's the equation of the tangent line. It has to have the slope, which is the first derivative, and it has to have that point on it. And sure enough, that 3 is equal to minus 1 plus 4. Yep, that's it. That's the equation of the tangent line. Now, if you're going with the point slope formula, that might have been a little easier to do. I don't know. But that was how you started it. Y minus y1 is equal to m times x minus x1. And when you plugged in the m of minus 1 and the y1 of 3, y minus 3 is equal to minus 1 times x minus 1, okay, then you have y minus 3 is equal to minus x plus 1, add 3 to both sides, and you get y is equal to minus x plus 4. So, I don't know. They're both easy, whichever way you prefer to do it. But it gives you the same slope, the same equation of the tangent line. Does that make sense? Okay. Done? All right. And let's see what they... Oh, look at that. They got y is equal to minus x plus 4. Good for them. All right. Now, this one I wish they had done on the slide set big time. The standard normal probability density function. Is that a mouthful or two? And you can see larsoncalculus.com for an interactive version of this type of an example. But anyway, I think I'll erase everything. I don't want to belabor this one too long because this is a rather complex situation here. But here you have f of x is equal to 1 over the square root of 2 pi times e to the minus x squared over 2. Okay? It says show that that probability density function has points of inflection when x is equal to plus or minus 1. Do you remember what points of inflections are?
I remember hearing the
What's
words
that?
before.
Okay, good. Yes, we've heard the words before. Okay. What a point of inflection is point of inflection is to a function as the max min, the extreme points is, okay, let me go back and say that again. Your extrema are to a function, you deal with the first derivative. Points of inflection to a function, you deal with the second derivative. It's where you set the second derivative equal to 0 and get the points of inflection. Does that ring a bell or make sense? Or
Isn't that where it's like changing?
yeah, that's where you change your you change your concavity. Exactly. Okay, and the concavity is where the second derivative is 0. Okay, so where it's changing its direction, that's your points of inflection. I mean, concavity is up or down, and where it changes, that's your point of inflection. And if concave up would be positive, concave down negative, where they change is your point of inflection. So it's where the second derivative is 0. Okay, so what do we do? Take a derivative, always a good choice of Cal 1 and the early part of Cal 2, take a derivative. Okay, and what would that derivative be? Well, that constant is still there, 1 over the square root of 2 pi. Okay? Now, take the derivative of that.
Why is the constant still there?
Because it's in front of a function. When you take the derivative of a constant times a function, you still have the constant. Yeah, if that was added to it, yeah, it would be like the last problem. 2 plus e to the minus blah, blah. Yeah, you lose it. But the multiplied by it, you still got it. Okay? So how would this go?
1 over root 2 pi, and then times
e to the negative
x squared divided by 2.
Right.
And then times a negative 2x.
How about just negative x? Because the 2's will cancel out, wouldn't they?
Oh, yeah.
Negative x. You buy that?
Yes, sir.
Okay. That's your first derivative. How about your second derivative? Okay, now things get a little more complicated. Why? That was merely a chain rule problem. This is a that was just a constant in front, so you just dealt with your exponential in the chain. Now you've got product rule. So that's got a variable in it too. When it was just a constant, you just wrote it down. But when it's got a variable in it, now you got to do a product rule. Okay? How do you do the product rule?
First times the derivative of the second.
Okay, so let's do the first times the derivative of the second. Do you want to leave the minus sign with the first? Okay, so minus x over the square root of 2 pi, okay, times the root of the second would be a
is the second derivative just the same again for the e's?
Yep, exactly. So what was that turn out being?
E to the
minus x squared over 2 times a negative x. Got it. Okay? So there's the first times the derivative of the second. And what's next? Plus
the second
okay, e to the minus x squared over 2, there's the second, times the root of the first, which would be a don't need it because that's the constant down there. Negative 1 over 2 pi, square root of 1 over 2 pi. See, that's just a number. pi is a number, 2 pi is a number, square root of that is a number. Those are just constants, okay? But derivative of, see, another way to write that would be minus 1 over square root of 2 pi times x to the first power. So its derivative is just that, right? Okay?
I'll try to make it harder than it'll be.
Yeah. All right. It's my job to make it hard. You don't try to usurp my job. Okay, here we have a minus times a minus, which is a plus. And we have an x squared over square root of 2 pi times e to the minus x squared over 2. And here we have a minus times a plus, which is a minus 1 over the square root of 2 pi e to the minus x squared over 2. Okay? Now, to make life a little easier, let's just factor out common factors, which is the 1 over the square root of 2 pi, right, times e to the minus x squared over 2, right? Those are common to both terms. And what are you left with? If you factor out the common factors, 1 over square root of 2 pi e to the minus x squared, what is x squared minus just 1, right? Because the whole term was there, right? Minus 1. Now, to find the points of inflection, we set that equal to 0. So set this thing here equal to 0. So I'm going to come up here, erase that little scratch work that I did here, okay, and set that thing equal to 0. 1 over the square root of 2 pi e to the minus x squared over 2 times x squared minus 1, and set it equal to 0. All right. How can we solve that?
Could we do it like individually?
Say again?
Well, set the x squared minus 1 to 0 and then set the other thing to 0.
Okay, yeah. That would do well. So you're saying the first part, either the first part's equal to 0 or the second part's equal to 0. So either 1 over the square root of 2 pi e to the minus x squared over 2 is equal to 0, or x squared minus 1 equals 0. Is that what you said? Okay. All right. Which you want to deal with first? First or the second? I don't care. Okay, first, what about it? Okay. Well, what can you tell me about it? One thing I can tell you is 1 over the square root of 2 pi is not equal to 0, right? It's just a number. It's not 0. Okay? So that's not 0. How about e to the anything? Is e never equal to 0? So the first is never equal to 0. All right, so it would look complicated, but guess what? That's never equal to 0. Because the exponential function is always greater than or equal to 0. So that's out of the picture. How about the second part?
X squared minus 1.
Yes, times. Oh yeah, what about it?
I'm assuming it doesn't equal to 0.
Is what?
Doesn't equal to 0.
You can set that equal?
I can say it doesn't.
Oh, you sure?
No,
Okay. What could you do with the x squared minus 1?
add 1 to both sides. And
Okay, we can try that. Let's see if you can do it without making a mistake. What would that give you?
x squared is 1.
Right?
So if you put 1 in there, it'd be 0.
Say again?
If you put 1 in for x, it'd be 0.
So x equal 1, is that what you said? That is correct. But that's not the question. The question is that the only, and I was afraid we might make an error if we did it this way, and we did. Okay. If we go back to what we had before, I'm going to have to talk with your pre-cal algebra instructors, because what would you do with a problem like this? And I haven't had you in a class before, right? If I have had you, I think I've asked this question before. What is the F word?
Factor.
Factor. Okay, now, yeah, I don't mean it to be offensive or anything, but you okay with it? Okay. What, can you factor this?
X plus 1.
You got it, and that's equal to 0. Now what can you do?
Now it's either plus 1 or minus 1.
Yes, x is equal to plus 1 or minus 1, which it was down here too. If you had remembered that any time you take the square root of both sides of an equation, you have to introduce a plus or minus. Remember that? Okay. Because x squared plus 1, x squared equal 1, that's true when x equals plus 1, or minus 1, they're both x squared. Okay. So if you had remembered that, that would have been a fine way to go. But it's so easy to forget the minus 1 here, that if you do it that way, you hardly can miss it. Go ahead and show that. So we've shown that at least potentially the 2 points of inflection with x equal plus 1 equal to minus 1, because that's where your second derivative is equal to 0. Okay? So that's all that we had to do there. Okay? Now, they show the graph in the book, and you don't have your book with you now, and my graph is going to look really ugly, but I can try to draw it for you. Can I go on and erase this? Okay. Here is what that standard normal probability density function looks like when you graph it. It's centered about 0, and it does this kind of number. Somewhere in here it goes from concave up to concave down, and somewhere here it goes from concave down to concave up, and that's at minus 1 and plus 1. Those are the points where that happens. You see, it's got to be concave up here, and got to be concave down there, and it has to be concave up there. The points where it changes is plus or minus 1. You know what we sometimes call that curve? Does the word taco ring a bell? A bell curve. That's what we think. Yes, it looks like a bell, doesn't it? Because it goes instantly in both directions there, and most bells don't. Okay. So if you just ignore that part, it looks like a bell. And that's a bell curve, and a lot of students like to be graded on that, so we put students on that grade up. No, that's your normal probability density function. And from that, you get your standard deviations and your variances and all that kind of stuff. That's getting into statistics big time. Okay, I think we're through with example. We've been using example 3 just for the white space. With that, finished example 6. Okay, let me get through this. All right, and then it goes into integrals of exponential functions. We've been doing derivatives. Now we do integrals. Now guess what? An integral is an antiderivative. And what was the derivative of an exponential function? Itself. So what guess might the integral of a differential or the antiderivative of an exponential function will be? Itself. Now, whereas we had the chain rule before that you multiplied by it, now the chain rule basically is going to divide by it. I'm jumping a little bit ahead. Let's get to the goodness, my knee hurts. I did way too much walking yesterday, and I did yard work on Saturday, both of which required knee work. So now, anytime I've been in a position too long, oh, that hurts to move. As soon as I walk around some, it feels better. Boy, coming out of the seated position is miserable. Or after walking a lot, getting into the vehicle was painful. Okay. So each differentiation formula in Theorem 511 has a corresponding integration formula. So the integration rules for exponential functions, if u is the differential functions of x, then certainly if it's just the integral of e to the x dx, what's that going to be?
E to the x plus
E to the x, then plus c, because that's an indefinite integral. If the derivative of e to the x is e to the x, the antiderivative of e to the x is e to the x, plus c, of course. Now, if it's e to the u, then what do we do? Certainly it's going to be e to the u, okay? But then you've got a plus c here too. So it's exactly the same thing because this is u that, yeah, these are just dummy variables, okay? Now, what made it look different before is you had in here, if you took the derivative of this and it was a function of x, that'd be e to the u times the u dx with the chain rule, okay? But you don't have to worry about this until you know what the u is, and then, or you are, and you have to fiddle with that. So, pretty straightforward, okay? You see, if you knew what the u was, then you wouldn't have a du here, you would have a d u dx, okay? But they didn't show it here, so you don't have to worry with it. You just do the e to the u. Now, if you didn't know what that function was, then you just put that function in here. It's pretty straightforward. Okay. So, let's do example 7. What's the indefinite integral of e to the 3x plus 1?
This is where we let u equal.
You can do that. Let u equal 3x plus 1. Then du is equal to 3. Need something else. Dx, exactly. You wrote it in differential form, so it's 3dx. Okay? And that would then indicate that, so you don't have a 3dx up here, you just have a dx, so you, divide by 3. Oops, I went to the wrong place. And let me clear out a little bit here. Okay, so du equal 3, du over 3 is equal to dx. Okay, so now we can write what we have here. This is the integral of e to the u, and now we have a 1/3. The dx is 1/3 du, so let's put the 1/3 on the outside and the du on the inside. Is that okay? Right? And what does that, and then what do we do with that?
1/3 integral e 3x plus 1.
Yep, 3, yeah, you got it. Okay, you were taking care of it at one fell swoop there. E to the 3x plus 1. Okay, now that's why I said before they didn't express it this way, but I did. Not that it's any better or not. This would just be e to the 3x plus 1 times, whereas when you're taking the derivative, you multiply by your chain rule part. If you divide by the chain rule part, what's the chain rule of this? Derivative of this? 3. So you divide by 3. So that's what I meant by that. They didn't show it in their example, but indeed that's what you got. But the way you did it it makes it very clear that's what you got. Okay? So, let me erase my scratch. Everybody got it? Erase that, and then let's see how they did it. If you, yeah, they did it the same way you did. Let u equal 3x plus 1, du is 3x. Then the integral of 3x, e to the 3x plus 1 dx would be the integral of 1/3 e to the 3x plus 1 times 3 dx. Yeah, I would have thought of doing that. This is making this 1/3, and this is e to the u du. Okay. I find it much easier to divide. Yeah, this works too. It's perfectly correct. Okay, because 1/3 of 3 is 1, and you got right the same thing you had before. But I just don't think in that way. But it's true. It's perfectly fine, and that would be 1/3 of the integral of du e to the u du, which would then be 1/3 e to the u plus c. Oh, we forgot to put plus c down, didn't we? Whoa! Okay, you let me get by with it, didn't you? Okay, but then you plug in what u is or u are, and it's and now they put it over 3. It doesn't matter which way you do it. E to the 3x plus 1 over 3 plus c, or 1/3 e to the 3x plus 1 plus c. Okay. So why in the world these flip forms? I don't know. But you see, if you're doing WebAssign, one or the other of these are going to count as right, and the other one they're going to count as wrong. But it's not wrong. It's perfectly correct. Okay. Any questions? Got it? Whoa! That's the last example they showed, and we have a few more to go, don't we? So let's go back and do example 8. Find the indefinite integral. 5x e to the minus x squared dx. Okay? Mm-hmm. What might we do with that one?
The u equals x squared.
Sounds like a good choice to me. Let u equal, did you say minus x squared?
Oh, yes.
Yes, I thought you did. Okay. All right. And here's Vince, right? Okay. All right, we've continued in 5.4 from where we left off last time, so we're now on page 346, example 8, bottom of page 346. All right. Well, what's your next step then? du is equal to?
Negative 2x dx.
Dx. I thought so. Okay. Now, notice what we have or don't have, okay? We certainly don't want the minus sign in there with the dx because it's not up there. So we could multiply or divide both sides of the equation by minus 1, so that'll make a plus here and a minus there. So minus du is equal to 2x dx. We really don't have a 2x dx up here either. We have a 5x. So what might we multiply this by to give us a 5x? Or we could just... Second?
2.5.
Yes, 5 halves. Exactly. Multiply this by 5 halves. And multiply this by 5 halves. Boy, I didn't leave enough room, did I? Okay. So let me rewrite that one. Okay. I should have allowed myself a lot more room there. Okay. So then minus 5 halves du is equal to 5x dx. Okay. Y'all okay with that? I skipped some steps by rewriting it, but we wound up same place. Okay. previous step in there. I should have done that. du is equal to minus 2x dx. And multiply both sides by minus 5 over 2, and that'll give you minus 5 over 2 du is equal to, and multiply that by minus, that makes it a plus, and 5 halves will make that a 5. Okay. So, what will your new integral be then? With the minus 5 halves in front. This part right here is your minus 5 halves du. 5x dx is minus 5 halves du, right? So there's the minus 5 halves here, there's the du there. Whoops. Messy u, but u nevertheless. Okay, let's try it one more time. du. Okay, got it. And then what do we have left? E to the u. Perfect. Okay, and what does this produce?
Minus 5 halves.
Minus 5 halves. E to the minus 5, no, minus x squared, right? Plus c, right? Be minus 5 halves, e to the u plus c, but u is minus 5 halves. Minus x squared. I get the 5 halves in my head, and I can't get rid of it. So there it is. Now, to clean it up just a little bit, see if I can do that without losing everything. Yep, I lost most of it. Okay. What you can do if you want to is check this by taking the derivative of this and see if you get your integral back. Take the derivative of this, you have minus 5 halves e to the minus x squared times a minus 2x, chain rule, minus 2x times minus 5 halves. The minuses go to plus, the 2's go away, and you get 5x equals 1, which is exactly what you got.
And so, how does the du go away again? And I know
How does the what?
How does the du go away again?
Okay. When you get it in this form, you're just integrating e to the u to u. It's just e to the u. Right? Okay. Now, if you're asked, that's the only place where it is to go away. Down here, it doesn't go away. It just this translates to this. Okay. Okay. And then when you do the integral of anything, you lose the du. You're integrating that, coming up with an answer. You're integrating this whole thing. Okay, the du is part of the integration, so the integral undoes the differential, basically. So it basically disappears. Is that adequate?
Yes, sir.
Whoa, that's gracious. All right, let's see what they got. This is example 8. Minus 5 halves e to the minus x squared plus c, done. Example 9, red-eyed. Everybody? Okay, top of page 347. Oh, there's 2 of them here. The first one is this one. The integral of e to the 1 over x squared dx. Yo. How might you proceed with that?
u equal 1 over x.
Ah, that sounds like a good one. Let u equal. Okay, then I'm going to write that a slightly different way too, which is x to the negative 1. Okay, then du is equal to, let's just take that second form. What would that be?
Negative x to the negative 2.
Right. One more little thing.
Oh, dx.
Dx. Very good. Now let's write that a slightly different way. Minus
X over 2.
yes, 1 over x squared. Right? 1 over x squared dx. Right? Just go back to rational form. See, here we went from rational form to exponential form, take the derivative, get after in the exponential form, but since our problem is in rational form, take that back. X to the minus 2 is 1 over x squared. Right? Move it downstairs and lose the minus sign of the exponent. Remember? Okay. All right. Now, do we have 1 over x, minus 1 over x squared dx? Positive. So let's multiply or divide both sides by minus 1. And we just don't worry about the middle one. You could if you wanted to, but that's not as important. We're just dealing with those two. So now we've got something we can live with. Okay? This will be the integral of e to the 1 over x would be e to the u. E to the u. And your 1 over x squared dx is minus du. So put the minus out here and the du in there. Right? All right, you ready to integrate that? This is a toughie.
Minus.
All right. E to the 1 over x. Yep. That's it. Plus e. My x looks a lot like a 4. I don't know why, but let me make it look less like a 4. There's your answer. Minus 1 over e to the minus 1. Minus e to the 1 over x plus c. And that c looks like an e. I don't know why, but let's clearing it up some. Whoops, not wrong. The pen didn't pick up. Okay. Make that look more like a C, less like an E. There we go. And let's see, is that what they got? Negative 1 over x plus e. Good for them. All right. Now let's do the B part. Because I took so much room with that part, I think I'll erase it and do the B part in its place. Is that okay? All right. So let's erase this and start back over and do the B part. The integral of sine x e to the cosine x dx. Okay, where would you begin on that? Sorry?
Cosine x.
Let u equal cosine x. Good choice. Then du is equal to negative sine x. What else?
Oh, dx.
Dx. Got it. And that looks a lot like you got up front, except for up top, except for negative sign. So let's make that a positive and that a negative. Now you got it. So this becomes the integral of say again?
Negative out front.
Negative out front. Perfect.
E to the U.
E to the U du. Perfect. Because e to the u is e to the cosine x, because u is equal to cosine x, and then your d minus du is sine x dx, so the sine x dx becomes a minus out front, du in the back. So, got it? What does that become?
E to cosine x.
Okay, minus e to the cosine x plus c. Done, done, done. And that's what they got to. Good for them. All right. They skipped example 10 too, so let's do example 10. All right, to erase. Okay. Page 347. Now we're near the middle of the page. Evaluate each definite integral. Now we're dealing with definite integrals. 0 to 1 of e to the minus x dx. All right. How would you do that? Help me. Okay, did I hear something?
So that would be u equals negative x.
Okay, that would work. Let u equal minus x, sorry. Started to put more down than what it was. Okay, minus x. Okay, then
U equals negative 1.
du is equal to what?
Negative 1.
Negative 1 what?
No, dx.
dx. Okay. And then,
We have a positive dx.
yeah, so let's negate both sides of that. You have negative du is equal to dx. And now what do we have? Oh, now what do we not do? Because we have, this is a definite integration, so we do have limits. So what do we need to do? Put the minus out front, integral from 0 to, if u is equal to minus x, when x equals 0, u is equal to 0, right? When x equals 1, u is equal to minus 1, right? And then you have your e to the u du, because you pulled the minus sign out front from down here. Okay? Now, do we usually integrate from right to left? In other words, from a 0 back to a minus 1. No, we don't. How do we change that?
Minus 1 on the bottom.
Yep. But if we do that, you lose the minus sign because you negate it. So that would be the integral from minus 1 to 0 of e to the u du. And what would that be?
So we lose the minus sign out front.
Yes, because, well, here's why. The integral from 0 to minus a of f of x dx is the same as minus the interval from minus a to 0. When you reverse the integrand, you negate the integral, right, of f of x dx. Okay, so when you reverse these two, you put a minus sign out in front, and that minus, change that minus to a plus.
Right.
Okay, is that all right? Okay. All right. Now, what is the antiderivative of e to the u du?
E to the negative x.
Okay. Okay. Don't go back now. Just use these things. If you change your terms of integration, if you wanted to go back, then you would have left them the same, 0 to 1. But if you changed them, and that's why I was asking if you wanted to change them, if you change them, then leave those in the place. Okay, and that would be e to the u evaluated from minus 1 to 0. Okay. If you're going back, then leave those as 0 to 1. If you're going back to x's, you go back to you don't even change them, just leave them. Okay, and what would this be?
And that would be e to the negative x.
Okay, e to the,
Oh, to the 0.
yes, e to the 0, which is 1 minus
E to the 1.
e to the minus 1. You plug in the minus 1, right? Once you've done your integration, which we did, integral of e to the u du is e to the u, right? Between these two limits, minus 1 to 0. So the upper limit is just e to the 0, u equals 0, and that gives you 1, minus the lower limit, e to the minus 1. Plug in the minus 1 for the u. There it is. That's what you got. Now, that's going to come up a number in the general range of 2/3, not exact. Maybe 0.62 or something like that. I can't remember exactly what it is. But it's not exactly 2/3, because remember E is about 2.7 something another. So this would be 1 minus 1 over 2.7 something, so that would be something a little bit greater than 1/3. So you subtract that from 1, so that would be something a little bit less than 2/3.
632.
About 0.632. Okay. Approximately. Okay? Okay with that one?
It's better we have a couple of these like this, because that's where I got confused on that one.
Right. Okay. Want to do another one now? The B one? All right. This will be the integral from 0 to 1 of e to the x over 1 plus e to the x dx. And what would be your first guess to do with that one?
U equal 1 plus E to the x.
That would be my first guess too. I don't know if it's going to work, but let's do it. 1 plus e to the x. Yeah, 1 plus e to the x. Then, say again.
EU
EU is equal to?
would be be
That would be e to the x, right? Because derivative of 1 is 0. And derivative of e to the x would be e to the x dx, right?
Looks like it's working out, though.
It sure does. So what does this become? Okay, we also have to, now, this time I guess I should ask, do you want to ignore your change of limits now, go on and do the integration, and then come back and put in, go back to x's and then just leave the limits where they are? Or do you want to change the limits as we go? It really doesn't matter. Just have to decide, but don't get them crossed up.
Let's just leave them this time because we changed them last time.
Okay, so you want to leave and not change your limits this time. Okay, so now we're going to treat it like an indefinite integral, and what will that be?
So you don't write your limits down when you say.
That's okay. If we're changing to u's and you put a du in there, then the limit should reflect the u. And right now they're reflecting the x's. Those are the limits on x's. So
we have to plug in the
you
1,
either do that now and then don't worry with changing back to x's because you're already going to be evaluating. Or don't mess with the limits now. Do the u's, and then when you get your answer, if you're going to change that back to x's, then put these limits back in. Pay your money and take your choice. You've already paid your money.
Let's go ahead and plug them in.
Plug them in, the new ones, the ones for you. Okay, let's do it. When x equals 0, what's u?
2.
2. Perfect. When x equals 1, what's u?
Right now, just 1 plus e.
1 plus e. That's it, exactly. Just a number. Just a weird looking number, but it's just a number. Okay, and then what is your integrand look like now?
E to the u du.
Du what? What did you say? I didn't hear.
Oh, e to the u du.
I don't think so. Your u is the 1 plus e to the x, right? And that's
du over u.
du over u. Got it. Okay. Now, what does that integrate to? Been a long time, maybe 4 days to a week.
Oh, is this where you subtract?
Do what?
Is this where you subtract your?
No, you would normally, except when you subtract, this would be a -1, and then a -1. No, you add 1, right, when you're integrating, and that would give you a -1 plus 1 would be a 0, so you have over 0, which we don't like to do. Oh my, so long ago. Antiderivative of 1 over u du. Okay. If you will look at the title of the chapter. No, it's on that page. At the top of the page. No, the previous page. Top of the page. What's the title?
Logarithmic exponential and other
Okay, and we're working with the exponential now. What did we do before?
logs.
Log, yes.
So.
Ring another Taco Bell. Okay. What is the antiderivative of 1 over u du?
See, I thought this is still there. You do the log.
Log U. That's it. Evaluated between 2 and 1 plus E. Okay? Which would be what? Those are the values for U that we're putting in. I'm going to write it on the line below if that's okay. Log of one plus E minus log 2. That's it. That's it. Don't have to go back to X's or anything else. That's it. What's that? Yeah, if you want to come up with a numerical answer, yeah, you can do that.
We can leave it like that, though.
You can leave it like that. That's an exact answer. Anything else you do is going to be approximate. And that's fine, okay? So remember, E is about 2.7, right? 2.7. So that would be log of something around 3.7 minus the log of 2. So it's not going to be a huge number, but it's going to be greater than. No, it won't, will it? Oh, yeah, because when you take log of those, they both come up pretty small numbers. So the difference is about 0.620, right? Good. All right. Same answer they got. Now let's do the C part. All right. C one is the integral from -1 to 0 of e to the x cosine e to the x dx. Whoa, ho, ho. What you reckon we're going to do with that? Let u equal e to the x. That sounds like a good, is that what you said? Oh, you said cosine e to the x. Let's just take it back a step and do it. U equal e to the x. Okay? Then, remember, the innermost part is the most complicated looking part of the problem. The e to x is fairly simple. It's the cosine e to the x is complicated. So the innermost part of that is your e to the x. So then, what would be the next step? du is equal to what?
E to the x.
E to the x what?
D.
dx. Hey, look at that.
Oh.
And what do we have now?
Now we have u cosine.
Okay. You have, no, okay. The e to the x dx is your du. Right?
Oh, okay.
Okay. So you have cosine u
D.
du. I think even we can do that one, can't we? What would that be?
Cosine.
Second.
This is where we plug in our.
Okay, you want to do the limits? Okay, let's do them. Okay, when x is equal to -1, what's u?
0.
Huh? When x is equal to -1, u is e to the minus
Oh.
1, right? And when x is equal to 0, u is equal to
1.
1. Okay. Now, Let's proceed with our antiderivative of cosine u. du.
Cosine e to the x.
What's that?
Cosine e to the x.
No, let's do the antiderivative of cosine. What is that?
Oh, negative sign.
Is it? It's just sine, isn't it? Because derivative of sine is cosine. So antiderivative of cosine would be sine, right? Now it's evaluated between e to the minus 1 to 1. And what would that be? Yeah, sine of 1 minus that's it. Weird. Okay. Now, what must you remember? What mode are you in? In calculus?
Radian.
Radian mode. You don't want to be in the green mode doing antiderivatives and things like that, because then you got chain rule to do with pi, all sorts of mess. You don't want to be there. When you're doing these, you're in radian mode. Okay? So it's sine of 1 radian, which is something a little bit less than 1/2 minus the sine of a pretty small number in radians, and that's going to be a fairly small number. But not too much, be it below 1/2, okay? Because e to the minus 1 is a pretty small number. You could do that on your calculator and see what you get. What's that? 0.842? 0.482? Yeah, that's it. Yeah, that's it. Perfect. Okay. So all three of those integrals were pretty small values because they were, they show the pictures in the book, the graphs of them, but you don't get a real good, well, yeah, that first one, if you continued the square 1 to 1, made a square 1 unit on the side there, you see that's less than half of, not less than half of it, well, it's less than a whole thing, a little bit greater than half of it. And you do the same thing with the next one, and you got a square of 1, and that's, again, a little bit greater than half of that square. And then on the third one, you fill in the square, minus 1 to 1, and that's a little bit less than half of that square. So yeah, those are all making sense in that sense, right? Okay. All right. That was example 10. Whoa, and that was all of 5.4, finally, okay? So homework exercises here, do any of the odds, 3 through 17. All those are at calcchat.com, 9's at calcview. Do any of the odds 19 to 23, they're all at calcchat. I would do all of 25 to 28, only the 25 and 27 will be at calcchat and in the back of the book too. Then do either 29 or 31. They're both at calcchat. 29 is at calcview. Any of the odds, oh, wow. 33 to 53, they're all at calcchat. 33 is at calcview. Any of the odds 55 to 61, they're all at calcchat. 57 is at calcview. Do 63, it's the only one like that. It's a calcchat. Do 65, it's a calcchat. Do 67, it's a calcchat. And then try 69, it's a calcchat. Then do any of the odds 71 to 77, they're all at calcchat. 73 is a calcview. Do any of the odds 79 through 85, they're all at calcchat. Do 87, it's at calcchat. Now they come up with a brand new formula for you here and ask you to do something with it. So number 89, if you want to, fiddle with that, you certainly can. Then do any of the odds 91 through 107. They're all at Calc Chat. 93 is at Calc View. Do any of the odds 109 to 117. They're all at Calc Chat. 111 is at Calc View. Do 119, it's a Calc Chat. 121, it's a Calc Chat. Either 123 or 125, they're both at Calc Chat. 123 is at Calc View. Do 127, it's a Calc Chat. Wow, do they have enough of these? There's true false, either 131 or 133 or both, and they're at Calc Chat. Then do any of the odds 135 through 143. They're all at Calc Chat. They should be anyway. Any questions? Now, they give some bases other than E and some applications. And I think what we're going to do is just do a slideshow of these. If you ever need them, by all means, check them out and do them. But we need to move on is really what it's getting down to. And I feel like we should have moved on even earlier, but this is all stuff that they're going to expect you to know later. I don't know, this summer, if you remember, we started later because most of the people in the class were beyond this, and we ran into this, and I think some people were a little lost because they couldn't recall this stuff because we hadn't done it. This book has a sister book that's calculus with early transcendentals. That mixes them in together rather than having them separate like this. And I think that would be the better book for us than this one. But I don't know. Anyway, let's move on to 5.5. And we'll do mostly PowerPoint show on this. I'll try not to stop and do too many examples with it. But I know I'm going to do some. Okay, bases other than E and applications. We're going to define exponential functions that have bases other than E, which basically, in most of the time, I think pre-calculus algebra books, they start with other bases and then introduce E, and that's so much easier. This one's starting with E and then going to the more difficult one, the other bases. So I don't know. We'll differentiate and integrate exponential functions that have bases other than E. I'll just show you how to do that and use exponential functions to model compound interest and exponential growth. Okay, so let's look at bases other than E. The base of the natural logarithmic function is, of course, the natural base of our number system, which is E. Doesn't feel like a natural base, but it is. That natural base can be used to assign a meaning to the general base A. So here's the definition of an exponential function to base A. If A is a positive real number, not equal to 1, okay? And you'll see why that's the case in a minute. Positive real number. Can't be 0, can't be negative. But it can't be 1 either. It could be a positive number between 0 and 1, but not 0 and not 1, or any positive number greater than 1. And x is any real number. Then the exponential function to the base A is denoted as a to the x. So let's just take some really simple examples. 2 to the x. When x is 1, that would be 2. When x is 0, that would be 1. When x was 2, that would be 4. X3, that would be 8. 2 to the whatever x1. Okay? Except that now the x can be any number. Any real number. X is any real number. It can be positive, it can be negative. Well, we can do a few negative numbers too. 2 to the 1/2 would be the square root of 2. 2 to the 1/3 would be the cube root of 2. So you can go that way as well. But that's using numbers. But remember, A doesn't even have to be an integer. It can be any real number. Can't be negative, can't be 0, and can't be 1. Okay? Now, here's why it can't be 1. If you put a 1 in here and raise it to any value there, it's always 1. Okay? 1 to any power is still 1. So therefore, that's why we leave off 1, because it's totally non-interesting. That's just a constant function 1. Okay? That's all it is. It's not a very interesting function. And if this were a 0, that would be very non-interesting too. That would just be the constant function 0. So we leave those two out. The negative numbers, then you'd have to exclude all even x's. And that would be a pain in the neck. So we just don't do any negatives either. Okay. But rather than plugging and chugging like I did there with just 1a, 2, or you could do any whole number a, but with this being any real number, here's what this is. Okay. E. I said I wasn't going to do this. I'm going to do it anyway. Okay. Let's just take. Oh, let me get my pen back. Okay. A to the x. Let's say it's some number y, right? Just to give it a name. Let's take the log of both sides. Yeah. Let's take the log of both sides. Natural log of that, and then that would be the natural log of that, right? Well, we know what this is, one of the rule of logarithms. That's x times the log of a, remember that one, is equal to ln of y, right? Well, I really don't care what ln of y was. I really want to know what y was. Remember, a to the x is equal to y. That's where we started with. I want to know what y is. So how to undo a log, but do an exponential. So let's exponentiate that and exponentiate that. Okay? Well, if you do that, e to the log y, that's simply y. And this would then be e to the x log a. Now, they put the log a in front. E to the ln a of x. Okay. Now, if you think about what this is saying now, and that's why they don't let, and here they go in the same thing I did. So we've already talked about that. A to the x, where a is any base, positive base, not 1. Okay, that excludes 0, includes negative, and now we have to say not 1. Okay. Then we can write that as an exponential function, e to the ln a of x. Okay, it just has a, it's not exactly e to the x, but it's e to the some multiple of x, and that multiple is ln a. So that's how you define a base other than e. Okay, a. It's e to the ln ax. Okay. So it can be defined as e, but you just have ln as a coefficient of the x. All right. Now, they go over a few things here. E to the zeros, or a to the zeros, perfectly legal, because x can be any real number. That's always 1. No matter what your base is, and remember, a can't be 0, okay? Can't be negative. But no matter what your base is, a to the 0 is 1. And then all your other rules hold. A to the x times a to the y is a to the x plus y. You did those way back in algebra somewhere. A to the x divided by a to the y is a to the x minus y. And a to the x raised to the y is a to the x times y. Okay. Now, that's just some general rules that still work for all these bases. So, now, this should be on another slide. It has nothing to do with the top, okay? But this is an application. And if you notice the title of this and applications, here's your first application. When modeling the half-life of a radioactive sample, it is convenient to use 1/2 as the base of the exponential model. So half-life is the number of years required for half of the atoms of a sample of radioactive material to decay. Okay. So here's the first example. The half-life of carbon-14 is about 5,715 years, which is a long time. Okay. Sample contains 1 gram of carbon-14. How much will be present in 10,000 years? With 5,700 years, only half of it would be left. So that's about another half of that. So it's just going to be, I think, a little less than a quarter. Maybe a little bit greater than a quarter. Okay. They're going to do it. I'll just let T equals 0 represent the present time. Let Y represent the amount in grams of carbon-14 in the sample. So your Y is equal to 1/2 times T over 5,715. Now, somewhere in the text they gave you the half-life formula, which they are skipping here. And I don't know why they did that, but you can go back and read this. But this is how you do half-lives. And when T is equal to that, the amount is reduced to half the original amount. So your time here, there's your T. That was 1/2 gram, like I already said. So when T is equal to 11,430 years, which is exactly twice that, the amount is reduced to a quarter, and so on. So basically, to find the amount of carbon-14 after 10,000 years, substitute 10,000 for T, and that would be Y is equal to 1/2 of 10,000 divided by 5,715. That's a little bit more than a quarter, which is about 0.3 grams. You can go through and do the math if you want to, and it's pretty straightforward math. Here is a graph of exponential decay. Remember, any exponential is going to go through the point 0, 1. Okay? So it went through there, and that's what it was. Your original time T equals 0, you had a full amount, 1 gram. Now you're down to 0.5 grams at 1 half-life, and you went on out here. At 2 half-lives, it would be at 1/4, 0.25, so this is a little bit greater than that. So that would be. Now, pretty exciting stuff, right? Where do we use this? Carbon dating. When they're doing fossils and things like this, they measure the amount of carbon-14 they have in it, and then do the inverse type functions to see how many years, how old that fossil is. Okay. The assumption here is that the carbon-14 concentration way back prehistorically was the same, approximately the same as what it is today. That, to me, is the biggest unknown in this whole thing. Now, the other thing that's pretty best known in it is when you get down here, way out here, your line is almost horizontal. It's still decreasing, but decreasing at such a slow rate. And if you measure carbon-14, but your measurement has a little bit of error in it, you don't know exactly because this is really gradual little stuff, then a little bit of error here represents an error here because it's changing so slightly. So it could be a little bit less than that, a little bit more than that, a little bit less than that takes you down here, more than that brings you up here. Your time error could be centuries, okay? Easily centuries, maybe multiple centuries. So therefore, even though it's based on a pretty good mathematical model, a little bit of experimental error there will throw you off by thousands of years, if it's old enough, okay? Small enough sample. And the smaller the sample, the bigger your error could be, right? So, percentage-wise. So, yeah, you could be in really serious trouble there. But the other error they never talk about is the assumption that the carbon-14 in the atmosphere of that many years ago is the same as it is today. We don't know that it was, okay? It may have been off a little because everything's been decaying, a little bit anyway. Well, they're basing this on that, but what if the base amount was a little bit different then? We don't know. So anyway.
Pretty interesting to think about that.
Yeah. Okay. So logarithmic functions to bases other than e can be defined much the same way as exponential functions to other bases are defined. So now we're taking the log of another base a. If a is a positive real number, not 1, and x is any positive real number, okay, then the logarithm of a function to the base a is denoted by log, the logarithm. The ln is logarithm natural, so that's ln. This is logarithm of base a, log of base a of x, and it's defined to be this. It's just what it is. It's ln of x over ln of a. I like to write it that way too, because see, the x is on top and the a is down here, so just write it as ln x over ln a. And that's what your the log base a of any number x can be transferred into ln's. Now, a lot of your calculators will have a log t, but that's always representing base 10. You can't throw in another base there. If it's base 10, you can use that key, the log key. But you can't use it for base 2 or 7.5 or pi thirds or any other base, which could be really wacky bases, but they're any number, okay? They could work, okay? But if it's any other base other than a, just change it to ln x divided by ln a. That will give you your every time. Okay. Now, here are some examples they give, and log in any base of 1 is still 0, okay? Every log function you draw, it'll have different curvature, but it's always go through the point 1, 0. Just like all the exponential functions go through 0, 1. Okay. And the log base a of x times y is the log base a of x plus the log base a. Same rules we had before. A log takes a multiplication and changes it to an addition. Right? We talked about that before. That's what slide is. Log of a base a of a number raised to the power is the power times the log base a of that number. Just like before, we did that in just the last example we did. And the log of a quotient is the difference of the logs. Okay? We did that. This is log of the product of the sum of the log of the quotient is the difference of the log. Okay. And this enables you to, if these were numbers that were enormously large or incredibly small, taking the logs of be able to do more reasonable, especially the large numbers. From the definitions of exponential logarithmic functions to the base a, it follows that if the f of x equal a to the x and g of x equal log a to the x are inverse functions of each other, and indeed they are. Okay, just wherever you say the base here, like this, the base down. All right, so here's the properties. Now, okay, they say properties of inverse functions. These are properties of your logs and their inverse functions. So if y is equal to a to the x, if and only if x is equal to log base a of y. So that's just saying these are inverse functions of each other. And a to the log base a of x is just x, because this is an exponentiation of the same base that you had before. Exponentiation of a log, as long as you have the same bases, they just undo each other. And log base a of a to the x, again, this is the base, here's the base, that's just x as well. Now, these are only for x's greater than 0. Why? You can only take the log of a number greater than 0. You can take an exponential of any number in the world. So this works for all x's. This works only for positive x's. So you can't take the log, any kind of log of a negative number. And the logarithmic function to the base 10 is called the common logarithmic function. So a common log of y is equal to 10 to the x if and only if x is equal to log base 10 of y. That's the LOG function in your calculator. Only the base 10, not any other. Now, do any of you have a LOG function with a little a under it? Or are they just all LOGs? I think they're all LOGs, aren't they? Yeah. That's base 10 only.
So is base 10 like a common?
That's because that's what we think our common base is. Okay, and John Napier is the one who came up with logarithms. These are the ones he came up with. Later, they were extended back to be natural logs, but he came up with this. And basically, if you write a number in scientific notation, 2.47 times 10 to the minus 3, the log of the 2.47 is some number between 0 and 1. Yeah, okay, I believe so. And then the log of 10 to the minus 3 would be a negative 3, so you just add those together because of the time, multiple. So you can do anything with it. You can do a lot of operations, very complex looking operations. If you change the logarithms, they become additions and subtractions. And that's why Napier came up with logarithms, to make some really complicated operations a lot simpler. That includes multiplying really large numbers. Made it simple by adding their logs. Okay. Is this worth doing, do you think? Here's how I would suggest that we do it. Okay, just to give you. Let's get 81 in the same base of 3. What would that be? 81 would be 3 to the what power? 4th power. So this would be 3 to the minus 4, right? So guess what x is?
Minus 4.
Minus 4. X equal minus 4. Okay. Now, this one may not be quite as obvious, but remember this is your base. So log base 2 of x is equal to minus 2 to the what power?
2 to the 2?
Second power, yeah, because 4 is, okay. So, that's just exactly like it was, right? And if you I said I wasn't going to waste a lot of time on this. If you raise this to the 2 to the this and do 2 to the that, okay, that probably should have been the way we did to begin with, yeah. This gives you x, right, because the exponentiation and a log, they undo each other, and this would be 2 to the minus 4. So this was not necessary for us to do. Just leave that as a minus 4. Okay? And 2 to the minus 4 is 1 over 2 to the 4th, which is 1 over 256, maybe. Let me think. 2 cubed is that? No, 1 over 64. 2 to the 4th, yeah. So that's the number. Okay. it's easier. I started off wrong on the other one. I was going to try to do it like I did this one, but that wasn't as easy. So let's just see what they get. I really found my way easier than what they did here. But that's going to be -4, which is exactly what we got, right? Okay. And the other one, this one, you do this, raise it to the second power, and that would be exactly, whoa, 2 to the 4th, 16, not 64. Yuck. Okay. Are we out of time?
Yes, sir.
All right, sorry about that. Okay. I wasn't going to do that many of these, but we just did 2. You know, well, okay, we'll just continue with the slideshow. I'll resist the temptation to do too many of the examples. Okay, we'll begin there next time. If you want to do some exercises here, you can, but that'll be only for your own cultural enlightenment. That would be any of the odds 5 through 9, any of either 11 or 13. They're all at Calc Chat. You can sketch the graphs if you want to. That's up to you, 15 to 19. And I think we even solved some examples before. No, we haven't yet. We'll leave those off for now. Okay, but you don't have to do those if you don't want to. All right, that's it.